Welcome to this complete engineering explainer on heat conduction. In this video we will build our understanding from the very first principles. We will start with the golden rule of heat transfer, move into conduction, then contrast steady state and transient behavior, and finally derive the elegant lumped capacitance method. By the end you will have both the equations and the physical intuition. Let us begin. The most fundamental rule of heat transfer is this. Heat always flows from a region of higher temperature to a region of lower temperature. Consider this wall. The outside face sits at 34 degrees Celsius on a summer day. The inside face is kept at 20 degrees by the air conditioning. Heat flows from outside to inside, driven entirely by that temperature difference. Now imagine the power cuts off. The air conditioning stops. Heat keeps flowing inward. The inside temperature slowly rises. As the two sides approach the same temperature, the flow weakens, and when both sides reach equality, transfer stops completely. No temperature difference, no heat transfer. Engineers write this as delta T equals 0, therefore Q equals 0. That is the golden rule. Now, let's try to understand the fundamental physics of conduction. Conduction is the transfer of thermal energy through a material without any bulk movement of that material. It occurs at the molecular level. Energetic, rapidly vibrating molecules, the hot ones, bump into their slower, cooler neighbors and share kinetic energy. This cascade propagates through the solid, one molecular collision at a time. A classic example, rest a metal spoon in a hot cup of tea. The spoon does not move. The tea does not flow through it. Yet within seconds, the handle warms up. That is conduction. In engineering we classify conduction into two regimes: steady state and transient. In steady state, the temperature at every point in the material does not change with time. Think of a wall that has been sitting between a heated room and the cold outside for hours. It has settled into a fixed temperature profile. This regime is governed by Fourier's law of heat conduction. Q equals minus K times A times delta T over delta L. Let us understand each parameter. Q is the heat transfer rate in watts. K is thermal conductivity, a property of the material. For example, copper has a K of around 400, while wood is only 0.15. A is the area through which heat flows, bigger area, more heat. And delta T over delta L is the temperature gradient, how steeply temperature changes across the thickness. Steeper gradient, faster heat flow. In steady state, because the temperature gradient is constant from one face to the other, the temperature profile through the wall is a perfectly straight line. Mathematically this means the second derivative of temperature with respect to position equals 0. That is the defining signature of steady state conduction. Now consider what happens when conditions are not fixed. Suppose outside temperature swings from 40 degrees in the morning to 50 degrees by midday. Or take this vivid example, a cold metal rod suddenly plunged into boiling water. At the very first instant the rod is cold throughout. 1 second later the outer skin has warmed dramatically, but the core is still essentially cold. 5 seconds later heat has penetrated deeper. The temperature at every single point inside the rod is continuously evolving with time. This is transient heat conduction. The equation governing transient heat conduction in one dimension is del squared T over del x squared equals 1 over alpha times del T over del T. The left-hand side describes how temperature varies across the geometry in space. In steady state this term was 0. In transient, it is not. The right-hand side is the new ingredient, del T over del T, showing that temperature changes with time. Alpha, the thermal diffusivity, equals K over rho times Cp. It tells us how rapidly a material equilibrates to temperature changes. High value of K or low value of ρ Cp means high alpha and heat diffuses quickly. High value of ρ Cp or low value of K means low alpha, and it means the wall accumulates heat and diffuses it slowly. This is responsible for the changing behavior of temperature gradient, which is constant in steady state. And this is responsible for transient behavior. Therefore we now have partial derivatives in both space and time. This is a partial differential equation, and analytical solutions exist only for simple geometries. For everything else, engineers turn to empirical charts or numerical methods. Inside the transient framework there is a beautifully simple special case. Consider dropping a small copper ball into cold water. Copper is an excellent conductor. The ball is tiny. Heat escapes from the surface quickly, but because conduction inside is so fast, the temperature remains nearly uniform throughout the entire ball at any instant. The ball has essentially one single temperature, and that temperature changes with time. This is the lumped capacitance scenario. Let's check whether our transient governing equation still applies here. The left-hand side, the second derivative of temperature with position, describes how temperature varies across the object in space. But in a lumped system, temperature is uniform throughout, there is no spatial variation at all. So this term becomes 0. If the left side is 0, then the right side, 1 over alpha times the rate of change of temperature with time, must also be 0. But that contradicts the entire premise of a transient problem. The temperature is still changing with time as the object heats or cools. So the standard transient conduction equation is no longer valid for a lumped system. We need a different physics, an energy balance over a control volume. Compare that to a thick block, where heat takes time to penetrate inward, leaving a temperature gradient inside it. An object like that cannot be lumped. Before diving into the math, let's just look at what this physically looks like. The instant the ball enters the oil, its temperature falls quickly. The gap to the oil temperature is large. As that gap shrinks, the rate of cooling slows down, and the curve flattens out. It approaches the oil temperature, but mathematically never quite touches it. This characteristic shape is exponential decay, and it is the signature behavior of every lumped capacitance process. Now let's derive it properly, starting from an energy balance. The energy stored inside the body is U equals ρ V Cp T. Heat leaves the surface by convection at the rate H times As times T minus T infinity. Our energy balance simply says, heat leaving by convection equals the rate at which the stored energy inside the body decreases. Setting the two equal gives our governing equation, HAS times T minus T infinity equals minus ρ Vcp dt dt. We rearrange to separate variables, temperature terms on one side, time on the other. Then we integrate, from the initial temperature Ti at time 0, to temperature T at time t. Solving this integral yields the classic exponential decay result. The grouped constant tau is called the time constant, ρ Vcp divided by HAS. A larger tau means slower cooling, a bigger, denser object, or weaker convection, takes longer to respond. So when can we actually trust this lumped assumption? We answer that by comparing two resistances to heat flow, the resistance to conduction inside the solid, and the resistance to convection at its surface. Picture it as a thermal circuit, just like an electrical circuit. Heat flows from the center of the object, through the solid by conduction, that is our conduction, then across the surface into the fluid by convection, that is our convection, and finally reaches the free stream, T infinity. Conduction resistance is Lc, the characteristic length, divided by K times As. Lc itself is volume divided by surface area. Convection resistance is 1 over H times As. The Biot number is defined as exactly this ratio, R conduction over R convection. The surface area AS cancels out neatly, leaving Bi equals H times LC, divided by K. A small Biot number means the conduction resistance is negligible compared to the convection resistance. Heat moves through the solid almost instantly, compared to how slowly it leaves the surface. That is precisely when the uniform temperature, lumped assumption holds. As a practical rule of thumb, if Bi is less than or equal to 0.1, the lumped approximation is considered valid. Our small, highly conductive steel ball easily satisfies this. A thick concrete slab, with low conductivity and a large characteristic length, does not, and would need the full transient analysis we saw earlier. Let us recap. First, the golden rule: no temperature difference means no heat transfer. Second, conduction is molecular energy transfer through a solid, no material movement needed. Third, in steady state, the temperature profile is linear and the second derivative is zero, governed by Fourier's law. Fourth, in transient conduction, temperature varies in both space and time, described by the heat diffusion equation with thermal diffusivity alpha. Fifth, when the Biot number is at or below 0.1, the lumped capacitance method applies. The object cools or heats as a simple exponential decay. In the next video we will tackle the harder transient case, where spatial gradients inside the object cannot be neglected. We will explore Heisler charts and introduce numerical methods. If this video helped you, please give it a like, subscribe, and share it with a classmate. Until next time, keep questioning, keep learning.